So it's a pleasure to have here Alessandro Palma, who is a senior researcher at the Gran Sasso Institute, and is one of the leading Italian experts on the estimation of the impacts of air pollution and climate change on several outcome variables. And previously he worked also on environment and economic development, and has consulted several prestigious institutions, including the World Bank, the Bank of Italy, and the FAO. So today he's going to present a new work on the impact of climate change of high temperature on cognitive performance. And so it's a pleasure to have you here. The floor is yours.
Okay, does it work now? I think so. Okay. So again, thank you, Francesco, for inviting me, and thank you to all for attending this presentation. I'm particularly pleased to be here today. And let me try to start the presentation. Oh. Okay. Okay, so today's presentation is about the effect of hot temperature on test score on students' cognitive ability. And this is a joint work with Daniela Vuri from the Department of Economics and Finance at Tor Vergata University and Rosario Maria Ballatore from the Bank of Italy. And so, first of all, let me give you a little bit of background for those of you who might not be very familiar with the topic. As you know, education and cognitive abilities are both key ingredients for human capital development and long-run growth. Is a strong predictor of lifetime income, for instance. And you also know that both internal and external factors such as pollution, but particular heat externalities more recently, have adverse impacts on cognitive abilities. And this because the disutility of effort increases as temperature gets higher. Just let me give you just the intuition of the physiopathological mechanism of these effects. The brain chemistry and electrical properties are strongly sensitive to heat. Think about that, the brain represents only about 2% of the human body mass, but it generates more than 20% of the body heat. Under normal condition, this heat goes into the bloodstream and is dispersed to the environment, but when it's hot, and the cognitive demand increases, individuals basically have more difficulty in accessing their brain. So it's just a temporary effect. And the effects are heterogeneous across different parts of the brain. As for instance, it has been demonstrated that the prefrontal cortex is the most sensitive part of the brain to heat. And basically, prefrontal cortex houses function of logical reasoning as a math reasoning. You also know that scientists expect a warmer world. We are increasingly struggling with heat waves and increasing temperature. European Union is largely exposed to this risk with a high regional heterogeneity, especially Italy is particularly exposed to heat waves. And up to the point that recently the World Meteorological Organization stated that we are entering a new norm characterized by extreme climate extremes, among which heat waves. And heat waves are becoming more and more frequent, especially in early spring. And this is particularly relevant for our work. Let me give you another piece of evidence by showing the European spring temperature anomalies over the long run. And these graphs shows the anomalies from 1950 to the most recent years. And as you can see, there's a large increase in anomalies of about, on average, 1 degree in spring in the last 5 years. So why it's so important to motivate this world to study the effect of temperature on human capital development outcomes like test score? First, because short-run temperature can impact and deteriorate the students' learning capacity, and these in turn can impact labor market outcomes and growth in the long run. Also, the temperature induced reductions in this cognitive ability, and this is particularly true in high-stakes settings, are able to determine our career in many steps of our life. Or just think about public competition, college admission, and so on. And also, last but not least, school assessment is often used to provide comparisons both across countries and within the same country across different areas. So just to mention, we know that we have a large north-south divide. So heat generates different externalities that have been studied in previous empirical works. Of course, there are studies showing how excess heat impacts health and mortality outcomes. I'm just mentioning papers related to human capital and labor outcomes. Of course, there are papers showing how heat waves impacts the suicides and mental health outcomes. Labor supply also is affected by extreme temperature and time use decision. Graphs even in needle show that workers change time allocation and reduce work time and devote more outdoor times as opposed to work times when temperatures reach about 27 degrees. Recently, Baer and Park and et al. Analyzed the effects of high temperature on workplace safety using accidents and injuries as an outcome. And there is, we know much less on the effect of temperature on human capital development outcomes. There is a small but influential literature showing these effects. We can broadly classify this literature in two streams. The first focus on realized performance, basically on the job effects, contemporaneous effects. And the other strand of literature focus on the realized learning, which is more strictly related to long-run effects. For instance, by analyzing the accumulated heat exposure during a year by using, for instance, a number of days above a given temperature threshold, and so on and so forth. So this paper provides different contributions to the previous literature. First of all, this is a large-scale examination using population administrative data, and this allows us to, of course, avoid sample selection in students that might sort into specific schools or specific grades. We studied the effect of temperature on students' performance in a low-stake setting, which is much more overlooked in the literature. The literature mostly focuses on high-stake setting. And above all, we are able to estimate the effect in a very standard environmental settings, basically due to the absence of air conditioning. We know that less than 2% of Italian schools are provided with air conditioning. And this is a bet, of course, for students, but this increases the credibility of our research design, given that we are able to examine the effect in a very standard environment. As a second contribution, we bring new evidence on the mechanism of temperature stress using new emotional outcomes, so outcomes that students perceive on the job while taking the test, using the students' questionnaires provided by Invalsi. We also estimate, of course, nonlinear effects, but also some heterogeneous effects across grades as a proxy of students' age. And finally, we study the mechanism induced by temperature and the relationship between test score, grade manipulation, and temperature. This is something new in the literature. Park has already studied the issue, but to the best of our knowledge, there's no evidence on the direct effect of temperature on cheating. So let me go through the data. Of course, if you have questions, just feel free to stop me anytime. We use, as a first source of data, we use the Invalsi testing program dataset. This is an administrative dataset, including students' achievement evaluation at different points of their school career. The same students is followed across different grades. We just use written tests during waves academic year 2012, 2013, up to the 2016, 2017. because in more recent times, test is administered using computer-based tests. We basically have a sample of about 10 million observations on which we, of course, apply some restrictions. Tests allow to examine two competencies, basically. Students answer a series of questions about logical reasoning for mathematics and lexical competencies for language, Italian. And data includes different grades, 2 and 5, according to issue level. This corresponds to primary school, and also 8 and 10 grade, which corresponds to upper secondary level, issue level 2. The outcome variable is standardized as an average of 0, a unitary standard deviation to allow comparability across grades and years. And also we benefit from these new behavioral outcomes deriving from the student's questionnaire. So these basically evaluate the student perception while taking the test. So whether the student is feeling anxiety while taking the test, or whether is worried about the test, and so on. We have this data only for grade 5 and 10. We align these administrative data. Yeah. To the standard test score? Yeah. I don't think so. I don't think so. So basically, it's something that we didn't do, but honestly, I don't know if this is possible. Okay, but I'm not presenting link data on this presentation, but that's a good question. I mean, to the extent you are interested in the contemporaneous effect on that day, this applies. It means that this question is registered on the same test date, so you might link just temporal. And basically, you have the same outcome on the same day. But I'm not sure if you can link, you can match students' questionnaire to each student's score.
My knowledge is that
you should.
Yeah, my knowledge is that you cannot, so that's why I was curious if you found a way.
No, not sure about that.
Okay.
Okay. We align this Invalsi data with weather data deriving from two main sources. The first is AgriForecast, deriving from the Joint Research Center. We have daily data on minimum, maximum, average temperatures, total rainfall, and wind speed. We complement this information with Copernicus ERA5 satellite data on relative humidity, which is a very important control. And so our treatment variable basically is both maximum temperature that enters the model both in a linear and nonlinear way, absolute temperature, and also bins of 3 degrees of maximum temperature. And we assume as a benchmark category temperature going from 20 to 22 degrees. We match this data at the municipality and test day level. Now, the identification is straightforward, given that we exploit the fact that test day are pre-assigned well in advance with respect to the actual test date. So basically, there's no manipulation risk. So there's no sorting of students into the treatment. So basically, students have no way to manipulate test dates. And the test is compulsory. And basically, we run a multiple fixed effect model in which we analyze both outcomes in math and language tests for students' I of different grades in different academic year. And also our treatment, as I said, is both linear and nonlinear. We control for any weather factors. Sorry, there's a typo. The B variable, the W variable is the P variable, okay? So weather control at the city level, and also a vector of students' characteristics when we use variation across school, the same school across test dates, okay? And we also control, given that we might have just mechanical correlation between temperatures and time and day in which the test is administered, we have to control for additional factors, for seasonalities, of course, years and grades, and day a week. But we don't need to control for exact test time, given that most of the time tests are taken at noon, which more or less corresponds to the maximum temperature in the day. So that's why we use maximum temperature as a proxy of temperature stress. We also observe for additional region time varying factors by including region time to fixed effects, and also we cluster the standard error to account for 3 factors at municipality level, with the spatial correlation across cities, autocorrelation of test score, and common assignment of the 3 at the municipality level. So basically, the residual variation in this model comes from variation in temperature across tests within the same students or within the same school. Okay, depending on whether we are assessing test score or heterogeneity across grades. Of course, we cannot exploit the same variation in the same students across grades when we run heterogeneous results. Yes, we follow students of a different grades.
Otherwise, people can hear you.
Grazie. Funziona? Okay. So why within the same student? Because you observe the students for several tests, or?
Yes, we do.
Okay, okay, didn't understand.
Yes, we do. Okay. So the first variation we use is within the same students across different grades and test dates. Okay. And when we run heterogeneous effects across grades, of course, we can exploit this information, and we use variation across test days within the same school.
But,
okay?
So, but you don't have a student fixed effect here?
Yeah.
You have student fixed effect?
Yeah, absolutely.
Because, okay, they're missing perhaps.
No, because this is just the general specification, okay? But the variation we use is just within students or within school.
Okay.
Okay.
So in a specification, you add also
either using school fixed effects or students fixed effects.
Oh, either one or the other. Okay.
Yeah, I will show you results that use both as a robustness check.
Okay. Okay.
So this residual variation, we interpret this residual variation as good as random for the reason I just said. Okay. Okay. So this is the variation we are using in the analysis at geographical level. This is average across test dates, all test dates in our sample. This variation in temperature goes from about 20 degrees up to 38 degrees. That's the maximum temperatures registered during test dates. And also on the right, I'm showing the variation used within the same school across different test dates. And as you can see, there's a huge residual variation that we can use for the analysis, okay, which is about more or less 30 degrees of differences in the same school on average. Okay, so let me present some basic results. Based on the results, when we run the model using linear temperature as a treatment, we observe a negative and significant effects in test score reduction in test score of about -0.004 standard deviation in language test, and this result is more than double in the case of math. And we observe an effect of about 0.01 standard deviation. This corresponds to, of course, a unitary increase in maximum temperature, which corresponds more or less to 1%. Okay, so each additional degree in maximum temperature lowered the standard deviation by about 1%, more or less. Yeah.
Yeah. Can I ask you a question about how should I read these numbers? I mean, the last one, for instance, 35, 39. Okay. Mm-hmm. So that number is the effect of having that temperature in a certain school or in certain.
No, that's the average in any school.
In any school.
The average given by the model. when temperature, maximum temperature moves from 22 degrees as a meter category to 35, 39 degrees. So that's the interpretation. So the reference here is 22 degrees.
Okay, but so that temperature is reached in, I guess, in the south or in some regions. So that effect is geographic.
Of course, there's a, I mean, this overall result is driven by some compositional effects, maybe by the south. We didn't explore this margin. We didn't run heterogeneous analysis by regions, which is of course very important in this case. Of course, the number of observations we have in each temperature beams, especially in extreme temperature, is relatively lower than the number of observations we have for milder temperature.
Yeah, which lead me to the next question, which is you show a graph in which you were plotting anomalies, but then in the analysis you're not using anomalies. You're using temperatures.
Just running,
and wouldn't it make sense to run the analysis on anomalies? Because I mean, a hot day in Bolzano is not a hot day in Messina.
Yes, it is, but it's, I think, more related to an additional part of the analysis, which is mostly related to adaptation process. I will show you some results about that. But of course, you're right. All the results can be interpreted as if we include deviation from the long run mean or mid run means, of course. But we prefer to, for a comparability reason with the literature, we just want to present results using temperature levels and then run some tests to test whether there is an adaptation process, whether the effects derive from past temperatures, exposure, and so on. Okay, but that's the effect of nonlinear effects of temperature in levels.
Sorry, I was out for 5 minutes, so I maybe missed. So every beam that you have is the increase with respect to a reference temperature, which is 2022.
No, Marzio, this is what I don't know your name.
Andrea.
What Andrea was saying before. This is not the difference. This is just we take temperature levels and we divide temperature levels in different beams. Just that. So the beam 3539 includes municipalities, schools during that all test days in which the temperatures during the test was in that interval, and that's it. There's no differences in this model.
And so you mentioned 2022, so I thought
that's the omitted category to basically to benchmark our the other beams, okay, in the model. So this should be interpreted as when the temperature moves from 2022 as omitted category to 3539, that's the effect on language and math tests. But there's no estimates on the difference in temperatures on deviation from the means. Okay.
Of the increase.
Yeah, it might depend also on that. Yeah, but there's no adaptation.
And also, as Andrea was saying, depending on the place, maybe, you know.
Yeah, no.
But Palermo, the average temperature is always 32.
Absolutely agree. That results might depend just for a small bunch of municipalities. It may be some specific dates, okay? But that's what we find as a baseline results. Okay, so this
just to follow up on the specification, because but you include municipality fixed effect, right?
Not in the student's fixed effect specification.
Okay. So this was the student fixed effect specification, not there. And another question: why in the control student level controls you did not add control for the family background? Because actually
we use it when we run the analysis at when we use variation within the same school. The analysis at the individual level, but using students' characteristics.
But this is the single most important. I mean, I believe in your estimates because I think they are orthogonal. I don't think that they are correlated temperature shock. So I believe in your estimates. But since it's the main driving force of test score, I mean, all the literature on test score.
Of course,
so
I agree.
I mean, it explain 15% of the variation. So actually, just to be safe, I would add because nothing will change, I'm sure 100%.
Now, of course, when we use student fixed effect specification, we don't use those
absorb this,
controls
of course.
that
Yes, of course you absorb
would
it.
be dropped in the analysis, but we use them when we run the analysis at the school level. Yeah, we have different controls, female, foreign, helpback students, grade keepers, and so on. Okay, those are the controls, individual controls.
But you don't have family background. I mean, I would suggest.
No, unfortunately.
You don't have the data because PISA data have family background. I thought that also in Balsi data. No?
I don't think we have family background. Maybe we have it, but maybe there are many missing data. But in any case, we might adjust some balance tests to check whether those characteristics can be used in the analysis that are orthogonal to the treatment. But I guess they are, given that just the residual variations given by shocks in temperatures across test dates, and that cannot be manipulated. So, but this is standard in the literature. Okay, that's the standard identification. Those graphs show much better. Can you visualize much better the effects, both in language and math? Most of the effect is in mathematics, in math tests, where we observe a drop up to minus 0.10 standard deviation when temperature is above 35 degrees. But the effects manifest also for milder temperature, specifically when temperature is above more or less 32 degrees. Okay. This is also in line with previous studies.
Sorry, out of curiosity, probably you're gonna talk about it later. The difference in significance between language and mathematics in terms of results, is it because, like, I would expect mathematics tests to be more cognitive, challenging for the students, and so, okay, thanks.
No, this is a well-established results in the literature. So logical reasoning is much more sensitive to heat, and all the papers disentangling the effect across subjects find more larger and more significant effects for tests related to cognitive, to logical reasoning. Yeah, that's the explanation. Okay, so this is something new. Given that we have this population data set, we are able to disentangle the effect across grades. And what we observe both in language and in math tests is that most of the effect comes from lower grades, which can be a good proxy of students' age. We find effects for grades 2nd and 5th, but we don't find any effect, any significant effect for higher grades. This is something that we should explore much more, having additional information, hopefully, but this might be given by kind of adaptation effects for more older students. Okay, the students, younger students might be much more prone to be exposed to heat stress than more older students.
Just following on the Andrea question, since you observe students in several years, why don't you control to try to explain this for the fact that they may had a past shock, weather shock, because of course they're autocorrelated.
No, we did it. We did it. I will show you. Let me show you in live, Francesco. Yeah. Oh, and these are the results. Maybe there's a question. Okay. Oh no. Okay. As the last baseline results, I'm showing you the effects about these new emotional outcomes. We have 4 outcomes. So whether the student is worried about before the test, whether the student is feeling that the test was not going well, and whether the students feels anxiety during the test, and whether the students feeling fine during the test. Only one of these is basically goes on the opposite direction, and this is clearly showed in the graph on the left. When we consistently find a different, basically significant and positive effect on the outcome dummy for these outcomes, basically the student's perception becomes negative when temperature gets higher, and also the sensation of feeling fine during the test goes down. And this only happens for lower grades, for grade 5, the grade for which we have this information. While we find any effect, any significant effect, or at least the effects much more confused in the case of higher grades and 10th grades. Okay, this is consistent with the heterogeneous effects across grades, and this also might explain the fact that there's an emotional mechanism generated by temperatures. Okay, now very briefly, we test additional alternative fixed effect model specification. We use variation school times grades. We use students fixed effects. We control for different kinds of fixed effect. The effect remains more or less stable and always very significant. Also, we test additional specification. For instance, we exclude mover students. In this case, the effects remain stable. We also test whether the effects survive when we control for when we include temperature in the previous days of the test as a like placebo test. We don't find any significant effect both in mathematics and language on the last column. And also, to answer your question, we test whether there's an adaptation mechanism. Now, the most important test we run is when we include both in a linear and nonlinear way exposure to temperature deviation in the same month over the past 3 years. Okay, so we run 4 tests. The first is when this deviation enters linearly the model. We interact max temperature in test day with this dummy indicating whether there is an excess of temperature in the past 3 years in the same month, and we can confirm the main effect, and we find no effect, no adaptation effect in this test. The same pattern we find when we use the nonlinear specifications to test adaptation. To extend this test, measure adaptation. We find no significant effects in any nonlinear specification on the model when we include temperature, excess of temperature going from 0 to 3 degrees, from 3 to 6 degrees and above. Okay, so it seems there's no adaptation process, and this strengthens the fact that we are measuring the performance effects and not the learning effects.
A very quick one. Here you are taking the excess over the last 3 years. I mean, this is not the norm about what you do in the literature. Typically, you take the excess with respect to 20 years. I mean, because basically you are taking the deviation from the mean over the last 3 years, but as you have shown in the graph at the beginning, most of the anomalies are concentrated in the last part of the sample. So basically, I guess that in this way you are not capturing an excess because you are comparing an already climate changed situation with.
Yeah, but this is not related to climate change. It's just related to temperature stress. And this, I mean, I couldn't include deviation temperature over the last 20 years, given that students have just born much more later. So there are students about 15, 12 years old, so it wouldn't make any sense.
No, but it's about measuring
deviation of the last 20 years. So yeah, basically, this just demonstrates that students have no capacity to the extent this test is well done. Students have no capacity in the short run. Yeah, I mean, I got the comment, but it's just to test whether students have adaptation capacity in a short run perspective. So whether last year was super hot and students just may be used to the fact that, oh, okay, I remember that in May last year was super hot. Maybe this year I'm going to be more careful in facing temperature stress, temperature anomalies, and so on. So this.
Okay, yeah. I had in mind a different story. I mean, how to measure deviation, very hot days. No.
This is an additional test we can run. So thank you for the suggestion. But we just measure whether this kind of adaptation measure the response. So. Okay. Okay. As an additional test. Oh, Julia, yeah.
Yes, I would like to ask, okay, so here you are controlling for the excess
heat temperature in the year before. But do you have lag for the days just before the test, for example, for the days in the previous week? Okay, no, because
We don't. I'm not showing the effect of the previous week as a treatment. I'm showing you the effect of the day before the test in the last column, and there's no, of course, there's no correlation between the previous day of the test, the true actual test day, and temperature and test score.
Because my idea was that if you have, for example, a period very hot, so kind of heat wave that lasts for more days, also the learning before the test could be compromised, and those are the...
Yeah, you're right. This part of the work is mostly devoted to test whether there's a effect on performance. We're not considering learning effects, but of course this is something that we might do using different treatment and exposure to temperature, maybe using a distributed lag model that we didn't use so far in this case. Yeah, but in any case, that's when we use the temperature the day before the test, we don't find any significant effects in this case. And the same happens when we test whether there is a short-run adaptation measure for students by interacting this with the deviation in temperatures in the past 3 years in the same month. Okay, now the last part of the work is something new in the literature. So we have this information about cheating, which is a score manipulation. And you know that the accountability, the increase in accountability also increase incentive to manipulate score, both for school students and teachers. And there is evidence of score manipulation, both in the United States and in Europe, but also in other parts of the world. In Italy, it has been estimated that cheating reduces test score by about 0.08 standard deviation in language test, and of about 0.11 standard deviation in the case of mathematics. And as you can see from this graph, so cheating is in the data. So when we use monitored class, that basically means that the class, there's an inspector in the class monitoring the test, there's a huge difference in the score. I mean, it's not super huge, but it's a visible differences when we compare monitored classes against non-monitored classes. This distribution basically shifts on the right for non-monitoring classes. It means that the score is much higher when classes are not monitored. Okay, this is something that is just roughly in the data. The prior is that cheating is a cognitive intensive task, like taking the test. So the prior might be that temperature increase incentive for cheating, but at the same time, cheating is itself an intensive cognitive ability task. So whether there is a direct effect or not of temperature on cheating is an open question, is an open issue. So first of all, let me show you the direct effects of temperature on cheating. This means that cheating enters the model as an outcome. And the pattern is similar to the one identified for test score. There's an invert U-shaped relationship between temperature and cheating. So basically, temperature, comfort temperature increase incentive for cheating, but when temperature gets higher and higher, this cognitive intensity task drops. Okay, that's what we find in the data. Okay, using the same model. Now we try to estimate also the effects of. Yeah.
Sorry, maybe I missed it. How do you measure cheating? I know it comes from.
Cheating is measured in Valsi measures. Cheating
okay, right,
provides a specific measures. Statistically measure of cheating along with the standard test score. Okay, so it's just officially using standard procedures and that are mostly technical.
So it's not very clear how to interpret how we can see the cheating here in this graph. Perhaps I missed something, because we have test score. I mean, it's the same.
No, sorry, there's a typo. This is not test score. That's
Okay.
cheating score. Okay.
Ah, okay. It's a
That's cheating score. Yeah.
Okay. So, and why in this specification you add also beans for low temperatures? Because in the other specification you don't have, or you,
No,
there
maybe
are-
it's
okay,
just
okay.
no. I didn't show you in the graph, but just that's the same specification that temperature is divided into 3-degree beams. So the effect is, the pattern of the effect is mostly similar to the one of test score. Again, sorry for the typo, but this is the effect on cheating, direct effect of temperature on cheating at different temperature beams. So there's an incentive for cheating up to very high temperature, and when then the effect drops. Okay. So now a natural question is, how does this impact test score? How can we estimate the net effect of temperature, net of cheating on test score? So this is something that we can do by just introducing cheating in the model, given that cheating affects both, temperature affects both cheating and test score at the same time. So we need an additional empirical strategy to solve this issue. And we follow the relatively recent strategy by Anglis, Battistini, and Buri, who instrument cheating using random monitoring assignment, basically inspectors visit that are randomly drawn from the ministry and are stratified also across regions, and to instrument cheating using this random variation in monitoring. So when we instrument cheating, we get a very large first stage effect. The F-test is very high and is super significant, but of course this makes sense given that I showed you before that cheating largely increases the test score. This way allows to estimate the net effect of cheating on temperature, on test score, net of cheating, of grade manipulation, of score manipulation. And what we find is that the effect of temperature is larger, is more negatively, is lower in the sense that it deteriorates much more test score. These effects peaks basically at minus 0.12 instead of 0.10 standard deviation. So the maximum effect is slightly higher, but above all, these effects manifest much earlier at milder temperature. And this makes sense given that when we measure the effect net of cheating, this grade, of course, deteriorates at milder temperature. We find also much more significant but very little effects on the of temperature on test score in the case of language tests. But again, most of the effects is when we consider testing for mathematics. So to conclude, let me give you some summary of these results. We find that higher temperature decreases test score. 1 degree increase in maximum temperature corresponds to about 1% drops in test score in mathematics, with respect to when temperature is measured in 3-degree beams, and we assume 22 degrees as a mid category, as a benchmark. This effect is much stronger for tests in mathematics than with language tests, and stronger for younger students, grade 2 and 5. And also temperature has an invert U-shaped effect on cheating. So the effect on cheating, the direct effect of temperature on cheating looks like to the one of temperature on test score. It appears to be invert U-shaped. And also the maximum effect of temperature net of cheating is slightly larger. It's about minus 0.012 standard deviation, but above all, it manifests much earlier at milder temperatures. So to conclude, what are the implications of these findings? So basically, with the world that is expected to warm in the future, in the near future, students might not be on an equal playing field, and must be. We should account for the geographical differences that basically are correlated with different exposure to temperature during the test day. So this basically leads to two possible policy proposals. The first is just to adjust dates to differential temperature exposure across different geographical areas. And of course, the second possibility would be to increase the quality standards of school facilities by providing school air conditioning, for instance. As I told you, less than 2% of Italian schools benefit from air conditioning. And basically, both interventions would lead students equal chance for human capital, for a more equal human capital development. So that's all. Thank you very much.
I have two questions. The first one is, I do not remember whether you mentioned the geographical distribution of schools across Italy, because given the amount of data that you have, one natural thing to do, in my opinion, would be to compare Valle d'Aosta with Sicily. Okay. The second question is cheating. If I understand correctly, as temperature is higher, there is less incentive to engage in cheating. Do I understand correctly?
At the highest temperature.
The highest temperature. Yeah. But you said that cheating is a intensive brain activity, and we saw that temperature, high temperature, negatively affects brain activity. So I would expect, you know, as the weather become hotter, you do less brain activity and therefore less cheating. So I do not understand. And what is the basis why temperature should affect the incentive to cheating? When it's cold, you cheat more. Is there a basis for this scientific basis?
Okay, that's a good question. Should I collect more questions, or do you prefer I answer?
Yeah, I would like. I have a few questions, but first I would like that if somebody else. Let's go first. Okay, I will do that.
Thanks for the presentation. Just a consideration, because when I think about teaching and education, I think that the effect of the temperatures will be more related to the overall year of the education. So if in a given year we observe an average value of the temperatures which is above the median, the average, at that point we will observe a different effect on the INVALS scores. I think we should look at that relation. So not at the day of the test, the temperature at the day of the test, but the average temperature on the overall year. And I think that that would provide also even more strong effects on the effect of the temperature. So observing the average temperature in the year and the effect on the INVALS test will provide, I think, additional results to your research. Thank you.
Okay, thank you.
Hi, again, thank you for your presentation. It was really interesting. I was in the first set of results, specifically the graph with the relationship with temperature and test scores. You could see that you have like a negative effect even for very low temperature between 0 and 2. Whereas when you instrument that, the U-shaped relationship somewhat disappears and the effect becomes positive for low temperature. Mm-hmm. Would you have any explanation for that? And additionally, it's a very broad and not specific suggestion, but I know that INVALS provides surveys done to principals and to teachers. So maybe there is something worth exploring with respect to infrastructure, or in the principals surveys, I think there are questions related to students' behavior throughout the academic year. So maybe there is something of interest.
Okay. Can I stop here? Just for the first set of questions, just to be sure that I answered the right question. Okay. Okay, the first question was about the cross-sectional comparison across schools and different areas. This is something that we can do, we want to do, but this would, I mean, the variation we're using now, Marzio, is the variation within the same school over time. Of course, we can run some heterogeneous effects. I'm sure there's a strong heterogeneous effects across different areas, but this is not straightforward because, as you can see here, temperatures are not commonly registered higher in the south. There are super high temperature even in the old Pianura Padana, and this is a relatively recent phenomenon. So basically in the last year, in the very last years, most of heat waves are registered in the northern areas rather than in the southern either. So of course we need to understand basically where those results come from which geographical areas. So we need to run some heterogeneous analysis. But I mean, the variation, I think that the most useful variation we need is not the cross-sectional variation across schools, but it's the variation within the same school over time that would be the same employed in the case of this heterogeneous exercise. But of course, I'm sure there are huge differences across geographical areas, also because students' behavior might be very different, even with the sort for individual time invariant student characteristics. And about cheating, yeah, this is a good question. I mean, we don't have a prior, there's no prior in the literature. This is something new. It's something relatively complex to capture for two reasons, I think. First, the cheating pattern is assumed to increase. I mean, when temperature gets higher, on one hand, there's an incentive to cheat, but at the same time, cheating is a high cognitive task. And this might be interpreted, I mean, this may work for the first part up to the 32, 34 degrees. Then the explanation might be that above a given threshold, given that cheating is a cognitive intensive task, when temperature gets higher, it drops. So, I mean, it's not easy to capture the entire process, the entire mechanism, given that this mechanism is highly nonlinear, has the mechanism of test score on temperature. Basically, you know that any study studying the effect of temperature finds highly nonlinear effects. And this is also the case, I think. But I mean, I have no prior on the direct effect of temperature on cheating. What we find, what is in the data is that we find this inverted shape and might be justifying saying that up to a point with comfort, let's say temperature, the temperature, I mean, reduces test score. Students, as I show you, is feeling negative sensation. This creates an incentive for cheating up to the point cheating can be no longer done because of higher temperature. So that might be a possible explanation. We need some more information to go through definitely into this mechanism. Not sure if I answer your question, Mats. But I mean, I have no strong prior about that. So this is something we find in the data and is relatively complex to explain for this reason, for the high nonlinearity effect. Okay, regarding the regarding the questions about different effects of performance versus learning, I think you are mentioning this difference. This is distinct difference in the literature. Of course, we can measure also, and I can also say that maybe this is not 100% precisely the effect of performance on the job. So by taking the test, maybe there's some part of variation we are losing that attributes the effect more to learning rather than on the job performance. But I mean, there are two distinct issues. On one hand, we can measure what's the accumulated effect of heat exposure over the year. And on the other hand, we can measure the effects while taking the test, which is not necessarily correlated with the learning effects. I mean, there are two distinct things. And this is a very net distinction in the literature. It might even be the reverse. I mean, we can also test only the pure effect of training by using the exposure during the test as a control in the model. It might be something that might be done, okay? But we are measuring two different distinct things. So to capture your suggestion, maybe we can make more robust the model, including some measure that capture learning effects, like exposure during the year and so on. But I mean, the literature is clear in this sense. The identification strategy is completely different because we are just using variation across test dates. So that should be just what the students perceive and the capacity of students to face with the test, which is not necessarily correlated with what the students have learned in the past months. Okay. This is also true because INVALSI tests are not necessarily designed to measure the learning effects. They're just measured to, and it also can change depending on the setting, whether you have a high stake or low stake settings. Okay, high stake tests are specifically designed to test both, but low stake settings basically are just a picture of the, of the capacity of students to reach specific educational targets. So, okay, we might explore also this margin by testing additional specification that accounts for training for learning effects. The third question is about the effect of colder temperature and school infrastructure, information on school infrastructure. We do have this information. We have information provided, by the ministry on school infrastructure. We didn't use this information with the exception of basically use the information that schools are not provided with air conditioning, but we basically draw this information from this data set. And also the effect of colder temperature. Also in this case, there is a well-established pattern, U-shaped pattern in the literature showing that negative effect also occurs when temperatures are particularly low. In this case, I would say that we are not able to capture the causal effects of lower temperature just because the environment is pretty much controlled, because there is heating systems working and when temperatures are very low. So I wouldn't interpret this result as causal. While it is much cleaner in the case of higher temperature because there's no air conditioning effect. When it's very cold, heating is working. So I have, no information to control for this very important confounding factor. And this might bias also this estimate. So, you're right, that's the well-established result in the literature that the temperature produces in that U-shaped. So both negative effects both for higher and lower temperature, okay? Which is something that we capture in our results. But I wouldn't interpret that as causal. I think I'm done with the first set of questions.
I also have a couple of questions. I mean, one is related to the discussion you had with Marzio. I completely agree with what Marzio said, and I think here to discipline a bit this idea related to which task is more cognitive intensive, which one is less, because then there is a race. You have limited time, you can spend your time either cheating or putting effort in the math task. Yeah. I think this part is very interesting, but to discipline this part, I think you will need to think about a ROI model where you have allocation of time across tasks, and then you decide, you know, because perhaps, because the surprising pattern is that you say that is, you increase the effort in cheating a bit when there is higher temperature, but then when you see the combined effect, when you do the IV, the effect is smaller. So actually it seems that I mean the effect on math score is smaller, you know. So actually is like unclear what's the mechanism here. And I think thinking about a possible, you know, theoretical framework also without writing down the model where you allocate tasks, and because math is more cognitive intensive than cheating, then you are going to choose cheating when it's very hot, you know. And so related to this, language and math tests are done the same day or in different days?
In 2 different days, I think.
Okay. So there is no allocation of time. Okay. So then I have a more general question that is related to how you want to sell the paper. I mean, clearly it's a very good paper. I think you can publish it really well.
Thank you.
And no, really, it's a very good paper. And I think that, I mean, what is a bit missing is you have like kind of 2 stories. I mean, this story about really investigating the cognitive mechanism of what happened with temperature that is related to this part here. That is very nice. And then you have another story that I think you have to develop more, as also Andrea and Marzio suggested, that is the story about regional inequality. I mean, about inequality in general. It can be across the region, across students. And on this part, I think the paper is weak, but because you didn't develop. So either you split the paper in 2, or you just try to put everything together, but in a kind of more coherent kind of way, and looking at which dimension of inequality, because then you can have inequality within across student within the school. We can have inequality across school. We can have inequality at a regional. So if you want to, and it's very interesting to see if this amplify or not inequality. You can run quantile regression. You can choose some dimension or RIF, some dimension of inequality, but you have to choose what you want to, you know, to sell here. Last point on policy implication: no air conditioning, insulation, finance by the next 100% super bonus, not for the private sector, but for the public sector, you know, for social housing, schools, insulation.
I totally agree with the last point. No, I mentioned air conditioning, Francesco, because in the United States, where this literature,
I know, I understand.
Any school is provided with air conditioning, so we have this much lower effect for this reason. Yeah.
I have one brief question. Have you looked at period time linked to the festivity? Like during winter, there is a lower temperature and there are festivity. Could be impact the attention of students in those periods. Like in the summer, there are higher temperature, and maybe students are less involved in studies, and as the same during winter period.
Okay. Okay. Francesco, I mean, you're right. This is pretty much work in progress. So, but all your points are well taken. Of course, we need to, I mean, better tell the story. There are different stories in this paper. The first is the net effect of temperature on cheating, but there is much more to explore in terms of these of inequalities, both the geographical and the socioeconomic status. One possible way to extract more information from the data would be to interact, given that we have information on the number of items and the order of items to which each student's answers. Maybe a good way to study whether there is an effect on cheating, or whether students prefer to dedicate the more time to more complex items, is to interact, or at least divide the analysis by item groups, or interact by the order of items and the complexity of the item and so on. Yeah, we have this information that we try to do something similar. I didn't show you today, but it's something that we can do. Okay, so thank you for the suggestions. And regarding the festivities, I'm not sure that I got your question very well. This analysis is run just by explaining the fact that the tests are taken in the same days, on those days, basically, so we have just a bunch of dates. So we have no information, but how can I say? This is not the effect of, again, learning over the year. We just have information on that test dates, and test dates are administered in early May and early June. So we don't have just information for that dates, for those dates. And so not sure if I got your questions, but of course we can control whether during festivities there are heat stress is particularly high, even though I'm not sure that is necessarily impact the effects in May or in June. You know what I mean? Yeah, but this is partially related to the fact that we are measuring performance and not learning.
So sorry, we have to close now the session. Until what time you are here? If somebody want to ask you a question in the afternoon, you are here a bit or not?
Not sure. No, I don't know.
What time you have the train?
No, that's 4:30.
Okay, so in case you want to talk with Alessandro, yeah,
okay.
No, in this case, because I didn't,
yeah.
Perhaps at 2:30 is going to be around in the library. If somebody wants to talk with him, it's going to be,
yeah, absolutely.
for
I'm happy
for 1 hour or so, and otherwise you can email him to follow up the discussion. It was quite interesting. Thanks to everybody. Thank you very much.
Thank you very much.